11 minutes. That is the total amount of time standing between a solar shockwave traveling at over 2,000 kilometers per second and complete unrecoverable collapse of the global power grid. Not hours, not days. 11 minutes from the moment scientists detect it to the moment it hits. And right now, the sun just fired. The shot is already in transit. A coronal mass ejection, a billion-ton cloud of magnetized plasma, is moving through space at speeds that make anything humanity has ever launched look like it's standing still. And the only early warning system Earth has is a single satellite, older than most smartphones, running on borrowed time with no backup. That satellite is called DSCOVR. And if it goes dark before that shockwave arrives, nobody gets a warning at all. By the end of this video, you are going to understand something that almost no one outside of NOAA and NASA knows in full detail. You are going to understand why 11 minutes is not enough, why the infrastructure protecting 8 billion people from the most violent force in the solar system is held together by a single point of failure, and why the people whose job it is to protect us know this, and have known this for years. But there is one number buried inside the DSCOVR mission data that the agency has never led with in a press release, a number that changes what 11 minutes actually means in practice, what it means for your city, your hospital, your water supply. We are going to get there. But first, you need to understand what is actually heading toward us right now and what it is capable of. Because the last time something like this hit Earth with full force, it happened before any of this infrastructure existed, before satellites, before power grids, before the internet. And scientists have spent over a century calculating what that event would do if it happened today. The number they came up with is not something any government has made a headline of. Stay with me. The sun is not a stable object. It is a churning, magnetically unstable ball of plasma that cycles through periods of relative quiet and extreme activity roughly every 11 years. We are currently inside what scientists call solar cycle 25, and it has been running hotter and more active than any predictive model forecast. The number of X-class solar flares, the largest category on the scale, has exceeded projections by a significant margin. Coronal mass ejections are not the same as solar flares, though they often travel together. A solar flare is radiation. It moves at the speed of light and hits Earth in 8 minutes. There is no warning possible for a flare. It arrives before the light that would have told you it was coming. A coronal mass ejection is matter, magnetized plasma. It is slower, which is why we have a detection window at all, but slower is relative. The fastest CMEs ever recorded have traveled at over 3,000 kilometers per second. The 1859 Carrington event, the most powerful geomagnetic storm in recorded history, produced a shockwave that crossed the distance from the sun to Earth in roughly 17 hours. Modern fast CMEs have done it in under 14. The event currently under observation is moving at approximately 293 kilometers per second. That puts Earth impact somewhere in the range of 15 to 60 minutes after DSCOVR detection. DSCOVR sits at a point in space called the L1 Lagrange point, a gravitational sweet spot approximately 1.5 million kilometers from Earth, directly between us and the sun. At that position, the satellite essentially hovers in place, held by the combined gravitational pull of Earth and the sun. It watches the solar wind constantly. When a CME arrives at L1, DSCOVR measures the magnetic field orientation, the density, the velocity. That data is transmitted to NOAA in real time and gives grid operators their warning window, 15 to 60 minutes. On a good day, with the satellite functioning, with the data stream uninterrupted, with the magnetic field of the incoming CME oriented in the worst possible direction, southward, which drives energy deepest into the magnetosphere, the operational response window shrinks toward its minimum. Power grid operators have stated publicly that they need a minimum of 15 minutes to begin protective shutdown procedures. Satellite operators need 30. At the lower end of the DSCOVR window, neither is achievable, but that is the scenario with the satellite working. Here is the scenario without it. DSCOVR was launched in 2015. Its intended operational lifespan was 5 years. It is now operating more than 6 years past that design life. The satellite has experienced multiple anomalies. In 2019, it entered safe mode due to a hardware fault and went offline for months. NOAA was forced to use older, less capable backup systems during that window, systems that provide less accurate magnetic field data and longer processing delays. That was during a period of low solar activity. This is not that. And the question that should be keeping grid operators up at night is not whether DSCOVR will eventually fail. It is whether it will fail during an event exactly like this one. Stay with me, because what comes next is where this stops being a space story and starts being something else entirely. Here is what a major geomagnetic storm actually does to infrastructure, and why the warning window is the entire ballgame. When a CME with southward-oriented magnetic field reaches Earth, it interacts with the planet's own magnetic field and begins driving enormous electrical currents through the upper atmosphere. Those currents induce voltages in long conductive structures on the surface, pipelines, rail lines, and most critically, high-voltage transmission lines. The transformers that sit at the nodes of the power grid, the massive building-sized units that step voltage up and down across the transmission network, are the most vulnerable component. They were not designed to handle geomagnetically induced currents. A severe storm can drive enough induced current through a large transformer to overheat and destroy the internal windings in minutes. These transformers are custom-built. They are not items that sit in a warehouse somewhere waiting to be swapped out. Lead times for replacement units run between 1 and 3 years. A single failed transformer can take down power to hundreds of thousands of people. A coordinated failure of dozens of them, which is what a Carrington scale event produces, is a different category of problem. In 2008, the National Academy of Sciences released a report estimating the potential impact of a severe geomagnetic storm on the United States. The figures in that report were not written for headlines, which is probably why they never became headlines. The estimate was that a major storm could cause $1 to $2 trillion in damage in the first year alone. Recovery time was estimated at 4 to 10 years, not weeks, years. That estimate was based on 2008 infrastructure. The grid has grown more interconnected and more digitally dependent since then, not less vulnerable. The Carrington event happened in September 1859. The geomagnetic storm it produced was so intense that telegraph operators reported receiving electrical shocks from their equipment. Some telegraph lines continued operating after operators disconnected the batteries entirely, running purely on the induced current from the storm. Aurora were visible as far south as the Caribbean. If that same event struck today, the electromagnetic environment it produced would be indistinguishable from a global EMP scenario in terms of grid impact. The transformers go first, the grid follows, and everything that depends on continuous electrical power follows the grid. Hospitals have backup generators. Those generators run on fuel. Fuel supply chains depend on electrically powered pumping infrastructure. Water treatment plants have backup systems. Those systems are not designed for multi-week outages. Data centers have UPS systems. Those systems measure runtime in hours, not weeks. The Cascade does not require a single catastrophic moment. It requires sustained loss of primary power to critical systems that were designed assuming restoration timescales of hours to days, not years. What does any of this have to do with DSCOVR in 11 minutes? Everything. Because every protective action available, grid operator shutdown, satellite safe mode, pipeline protection protocols, every single one of them is time dependent. The infrastructure to survive the storm exists. The procedures exist. The trained personnel exist. The only thing those procedures require to function is time. And the only thing standing between the storm and the clock is one satellite that is operating past its expiration date with no confirmed replacement. There is a replacement mission called IMAP. It launched in 2024, but it is a science mission. Its space weather monitoring capability is limited compared to DSCOVR. The operational gap is real, and it is not closed. Here's the part of this story that nobody seems to want to say clearly. The scenario where DSCOVR fails during a major CME event is not a fringe risk. It is not a tail risk thought experiment buried in an academic paper. It is a documented, modeled, publicly acknowledged concern at NOAA. The agency has said so in budget justifications submitted to Congress. In those documents, the language is careful, but the meaning is not complicated. DSCOVR is aging, the backup systems are less capable, and there is no funded successor with equivalent magnetometer capability in operational orbit. Congress received those documents. Funding for a DSCOVR successor has been proposed, discussed, and deferred multiple times across multiple budget cycles. This is not new information. It has been available to anyone willing to read federal agency budget justifications, which is a very small number of people. In the meantime, the satellite keeps flying, the solar cycle keeps climbing, and the CMEs keep coming. Now here's the moment in this story where the math gets personal. You do not need to be near a power plant or a major transmission hub to feel the effects of a large-scale grid failure. The average American household has enough food for roughly 3 days without resupply. Municipal water systems in most cities lose pressure within hours of pump failure without backup power. Cellular networks run on towers with battery backups, typically rated for 4 to 8 hours. After that, most communication infrastructure goes dark. The ability to coordinate emergency response, distribute resources, or even determine the scale of damage depends on communications infrastructure that does not survive extended power loss. The 2003 Northeast blackout lasted approximately 2 days and affected 55 million people. It was caused by a software bug and a series of cascading failures in the grid. No solar involvement whatsoever. The economic impact was estimated at $6 billion. Restoration took days, not weeks, and it drew on repair resources and mutual aid from unaffected regions. In a geomagnetic storm scenario severe enough to cause widespread transformer failure, there are no unaffected regions to draw from. The mutual aid network fails at its first assumption, that somewhere else still has power. This is where the warning time stops being a number and starts being a policy failure in real time. The difference between 15 minutes of warning and 0 minutes of warning is not a 15-minute difference in outcome. It is the difference between a managed emergency and an unmanaged catastrophe. Grid operators who receive 15 minutes of warning can begin controlled load shedding, deliberately cutting power to portions of the network to protect the transformers. The lights go out, but the hardware survives. Restoration takes hours to days. With 0 warning, the storm hits a fully energized grid. The induced currents have maximum effect on energized transformers. The hardware does not survive. Restoration takes years. By the way, and this is the part that most coverage of solar storm risk quietly skips, the Carrington event was not even the most energetic solar outburst scientists have evidence for. Ice core data analyzed over the past decade has identified isotopic signatures from a solar particle event in 775 AD that appears to have been significantly more powerful than Carrington. We have no instrumental record of it. We have no way to know exactly how it unfolded. But the physical evidence of what the sun produced that year is preserved in the chemistry of ice that fell on Greenland and Antarctica 12 centuries ago. The sun is capable of more than Carrington. We have proof of that. We just do not have a satellite rated to survive what it would take to warn us. So let's close the loop on why 11 minutes is the specific number this comes down to. The current CME under observation is moving at approximately 1,293 kilometers per second. At that velocity, from the L1 point where DSCOVR sits, the shockwave reaches Earth in roughly 19 minutes after satellite detection, at the faster end of the warning window. By the time DSCOVR measures the magnetic field orientation, transmits the data, NOAA processes it, and issues the alert to grid operators, the usable response window is down to approximately 11 to 15 minutes. At the threshold, barely inside the minimum action window for grid protection, but that window assumes everything works. DSCOVR's data pipeline involves transmission to a ground station, relay to NOAA's Space Weather Prediction Center, automated processing through software systems, and then alert dissemination. Every step takes time. Every step has a historical failure rate. Under normal operations, with a healthy satellite and clear data, the system functions within its design parameters. Under stress, an anomaly, a data dropout, a processing delay, the effective warning time compresses further. The 11-minute figure is the optimistic end of the operational range. The pessimistic end is 0. The open loop that's been running through this entire video is the question nobody asked at the press conference. What happens to the grid if DSCOVR goes dark during this event? The honest answer is that grid operators shift to watch and wait mode. They monitor ground-based magnetometers, instruments on the surface that can detect geomagnetic disturbance after it begins. Ground-based magnetometers do not provide the same advance warning as L1 measurements. They tell you what is happening as it is happening. By the time a ground-based magnetometer shows transformer-threatening induced current levels, the response window for protective action on large transformers may already have closed. There is a working group inside NOAA called the Space Weather Operations Research and Mitigation Initiative, SWARM. It was established by executive order in 2015 and renewed in 2019. Its mandate is specifically to coordinate federal agency preparedness for extreme space weather events. It has produced reports, it has published recommendations, it has identified the DSCOVR successor gap as a critical infrastructure risk. Those recommendations are on record. The gap remains, the satellite is older, the cycle is higher, the CME is inbound. Here is the final number, the one that actually puts the full picture together. DSCOVR cost approximately $340 million to build, launch, and operate over its initial design life. The National Academy of Sciences estimated Carrington-scale storm damage at $1 to $2 trillion in the first year. The ratio of insurance to potential loss is roughly 1 to 3,000 or worse. For context, the U.S. spends approximately $900 billion annually on defense. It has spent a fraction of a single F-35's unit cost on maintaining its primary solar storm early warning capability past its designed end of life. The math on that priority is not comfortable. The solar shockwave is real, the timeline is real, the satellite is real and aging, the warning window is real and shrinking. None of this is speculation or worst-case scenario storytelling. Every number in this video comes from NOAA documentation, peer-reviewed space weather research, National Academy of Sciences reports, or direct mission data. The gap between what exists and what is needed is not a secret. It is a publicly documented, politically deferred infrastructure failure, waiting for the wrong CME to arrive at the wrong moment. What makes this different from most catastrophic risk scenarios is that the solution is known. It is not complicated. It is not technologically impossible. It is a satellite, a funded, designed, launched successor to DSCOVR with equivalent or better magnetometer capability at L1. The cost is measured in the hundreds of millions. The benefit is measured in trillions and in lives, and in the difference between a recoverable emergency and a years-long civilizational disruption. The gap exists because it has not been treated as urgent. Events like this one are what force the recalculation. The CME currently heading toward Earth will either hit DSCOVR's detection window cleanly and give grid operators their warning, or it will not. By the time you finish watching this video, we will be closer to knowing which. The satellite will either hold or it will not. But this event, whatever it produces, is not the last one. Solar cycle 25 has not peaked. The sun is not done. And the early warning system protecting the infrastructure that every hospital, every water treatment plant, every communication network depends on is a single aging satellite with no confirmed replacement, and a detection window that, at its minimum, gives the people who need to act 11 minutes to save the grid. If this kind of analysis is what you come here for, the numbers behind the headlines, the infrastructure story underneath the event, subscribe. Share this with someone who thinks space weather is an astronomy topic and not an infrastructure one. And if you want to go deeper on what a Carrington scale event actually looks like hour by hour for a modern city, that video is next.